SwayamPrabha. Digital India. Educated India.
Welcome to lecture 23 of the course on multivariate data mining, methods and applications. The title of this lecture is Multi-layer Perceptron. In the last lecture, we have discussed the architecture and learning rule for the single layer perceptron. The limitation of single layer perceptron is that it fails when the decision boundaries are non-linear. So, it is not able to handle non-linear problems. If the relationship between input variables and output variables is quite complex, it is non-linear, then we cannot use it. In that case, we can use multi-layer perceptron. Multi-layer perceptron is actually consists of an input layer, then it also has an output layer. In between the input layer and the output layers, it has many hidden layers. Hidden layers consist of several nodes, and then at each hidden layer for a particular node, we compute the weighted sum of inputs which we obtained from the previous layer, and then we apply the activation function and ultimately we get the output. And this output is the input for the next hidden layer. So, this is how multi-layer perceptron works. So, in this lecture, we will discuss the architecture of multi-layer perceptron and its learning rule. We will also discuss the multi-class classification problem in this lecture. So, multi-layer perceptron. A single layer perceptron cannot distinguish if the classes are not linearly separable, and it cannot handle complex and massive data. If you have massive data and the relationship between input and output variables is not so simple, it is quite complex, then single layer perceptron cannot handle this kind of problems. Multi-layer perceptron can work with non-linear functions. So, if the relationship between inputs and outputs is quite complex, it is a non-linear function, then one can go for the multi-layer perceptron. Multi-layer perceptron has one input layer from where the input enters, and then corresponding to each input variable, there is one neuron or one node, and then it has one output layer. In output layer also, we have a single node corresponding to each output. Then in between the input layer and output layer, it can have any number of hidden layers, and each hidden layer can have any number of nodes. So, then it combines neurons together, so that outputs of some neurons are inputs of other neurons. So, initially you have the input layer. In input layer, we do not do any computation, except if you want to use some kind of transformation or you want to use some scaling, etc. and then we combine the neurons together, and then we move to the next layer. Next layer may be some hidden layer. So, output of input layer goes to some hidden layer, and then we move further, say output of one hidden layer may be input for the next hidden layer, and so on. Then every node in the multi-layer perceptron also uses an activation function. So, not only we take the weighted sum, but we also apply some activation function. So, suppose this is your input vector x equal to x 1 x 2 x r transpose. So, this is r cross 1 vector, which is consist of r input variables, and then y is y 1 y 2 y s transpose is s cross 1 output vector, which is consist of s output variables. Then multi-layer feed forward neural network or perceptron maps input vector x to output vector y with hidden variables arranged in layers between input and output. So, in between you have some hidden variables which are arranged in different layers or different hidden layers. So, suppose we consider multi-layer perceptron with a single hidden layer, and then suppose r is equal to 3, that is we have 3 input variables x 1, x 2 and x 3. And then we have one hidden layer, and this hidden layer has 2 nodes. So, then we have this output layer also has 2 nodes. So, what we do? We combine x 1, x 2, x 3 with weights beta 1 1, beta 2 1, beta 3 1, and then we get this sum, and then we apply this activation function. So, we reach to this node. Of course, we also take x naught equal to 1, and beta naught 1 is the term corresponding to the bias or the weight corresponding to the bias. Similarly, we combine x 1, x 2, x 3 using the weights beta 1 2, beta 2 2 and beta 3 2. And then we take this summation, means beta 1 2 x 1 plus beta 2 2 x 2 plus beta 3 2 x 3. And then we apply this activation function. Of course, we also take beta naught 2, which is the term weight corresponding to the bias term, and then we apply this activation function. So, we get some value here, we get some value here, but basically we are not interested in the output here. And then we combine the output which we have is received here or the output which we have received here to get this output layer. So, for this output layer actually the output corresponding to this hidden layer becomes the input from this layer. And then we apply the activation function g here, and ultimately you get these outputs. So, this is your input layer with 3 nodes, then you have one hidden layer which has 2 nodes, and then you have this output layer which has 2 nodes. In general, suppose you have r input nodes and S output nodes. And suppose you have L hidden layers, and Tj is the number of nodes in the jth hidden layer, j equal to 1 to L. So, capital L is the number of hidden layers, and in the jth hidden layer we have Tj nodes. So, in the previous example we had R equal to 3, S equal to 2, T equal to 2, of course, L is equal to 1. We have just a single hidden layer. Then there are two computational layers. Remember, in input layer we do not do any computation, except we use some transformations like scaling, etc. So, basically we are doing computation in two layers, one hidden layer and one output layer. Further, artificial neural networks can be used in classification or regression problems. So, ultimately it depends upon the value of y. Say if y is continuous, then it is a regression problem. If y takes discrete values, say suppose y takes binary values, then it is a classification problem. So, again you have input values which enter through the input layer. Each hidden node computes an activation value, say weighted average of its input values plus a constant. So, you have weighted average plus this constant, and then each output node computes an activation value, weighted average of inputs to it plus a constant. And then activation values are filtered through an activation function. So, we get this sum, and then we filter this sum using this activation function to form the output value of the neuron. So, ultimately you get some output value. Then the output for this layer becomes input for the next layer, and we further repeat the same process, but of course with different weights, and you may have different activation function also, and ultimately you get the final output. Fully connected network. In fully connected network, all input nodes are connected to nodes in the first hidden layer. All nodes in the first hidden layer are connected to the nodes in the second hidden layer, and so on. At last, all nodes in the last hidden layer are connected to the output nodes. So, this kind of network is called the fully connected network. Partially connected network. In partially connected network, some of the connections are missing, and you may set all those missing connections as 0. So, if the connection between two nodes is missing, then you say that those nodes are not connected, or the network is not fully connected. Of course, if the network is partially connected, you can write it in the form of a fully connected network by setting the weights corresponding to the missing connections to 0. So, you set the missing connections weights equal to 0, and then you may represent a partially connected network as a fully connected network. Then multi-class classification rule for k classes. Say y takes value 1 or 0, y is a binary variable. Then there are s equal to k minus 1 nodes taking values 0 or 1. So, hidden layers are not part of input or output nodes. So, basically your output has k classes and y corresponding to a particular class takes value 1 if the observation is classified into that class, otherwise it takes value 0. Now, suppose we consider a single hidden layer. So, these are your input nodes. So, x m equal to 1 to r. So, ultimately you have r input variables, and then you have just one hidden layer, and that in that hidden layer you have t hidden nodes. So, z j equal to 1 to t, and then you have s output nodes y k equal to 1 to s. Now, suppose u j is equal to beta naught j plus x transpose beta j. So, first what we do? We combine the input variables using the connection weights. Of course, we also take this bias term, and then V k is equal to alpha naught k plus z transpose alpha k. Then these u j's and v k's, these are the activation values. And then how we get these jets? So, if we combine the input variables, then we get u j's, and then we apply this activation function, say f j u j for j equal to 1 to t. So, you get z j, and then mu k x is equal to g k v k. So, ultimately what we are doing, first we are combining the input variables, and then we get this activation value, and then we apply this activation function to get the values corresponding to the hidden layer, and then we get V k by combining the values which we obtain from the hidden layer, and then we use the activation function g k to get the final output. And ultimately you can write g k v k in as a function of x also. And suppose you write g k v k equal to mu k x. Now, suppose beta j is equal to beta 1 j, so on beta j transpose, alpha k is equal to alpha 1 k, so on alpha t k transpose. So, actually alpha k here is t cross 1 vector of parameters or weights, beta j is r cross 1 vector of weights. Then the kth output node can be expressed as, say y k equal to mu k x plus epsilon k. Epsilon k is the error term. Now, this is basically just like a regression model, yk equal to mu k x plus epsilon k. And we may assume that this epsilon k follows normal distribution having been 0 and variance sigma square k. Now, we try to write the form of mu k x. So, how we get mu k x? We combine the inputs, then we apply this activation function. Further, we use these weights, means these are the values which we get in hidden layer, and then we combine these values of the hidden layer using these weights, and then we apply this activation function, and finally, you get mu k x. So, f j is the activation function for the hidden layer of nodes, and it is usually taken as nonlinear continuous functions with sigmoidal shape, that is logistic or 10 hyperbolic function. Actually, both logistic function or 10 hyperbolic function have sigmoidal shape. And then usually we take g k, which is the activation function for the output layer of nodes. We take it as linear if the problem is the regression problem, or sigmoidal if your problem is the classification problem. Then we try to write equation 1 in matrix notations. So, suppose B is T cross R matrix of weights between input and the hidden layer. Ijth element of B is beta ij, and A has jkth element alpha jk. So, A is S cross T matrix of weights between hidden layer and output layer. So, B is the matrix of weights between input layer and hidden layer, and A is the matrix of weights between hidden layer and output layer. And then beta naught is the vector of bias corresponding to the hidden layer, and alpha naught is the vector of bias corresponding to different nodes of the output layer. Then using these notations, we can write equation 1 as mu x equal to g alpha naught plus a f beta naught plus b x. So, you can write mu x in this form. Again, this f is T cross 1 vector of nonlinear activation functions corresponding to the hidden layer, and G is S cross 1 vector of nonlinear activation functions corresponding to the output layer. And suppose you take S equal to 1, then for S equal to 1 you have just a single output node. Then suppose sigma dot, this is sigmoidal activation function corresponding to the hidden layer. So, corresponding to the hidden layer we are taking sigmoidal activation function, and then suppose the activation function corresponding to the output layer is linear. So, G dot is linear activation function corresponding to the output layer. Then mu x is equal to alpha naught, G is linear, plus summation j equal to 1 to t alpha j sigma beta naught j plus m equal to 1 to r beta m j x m. And then we get the single layer perceptron. So, single layer perceptron is a special case of multi-layer perceptron. Now, if both g and sigma are linear, then mu x is a linear combination of the inputs. So, here if you take sigma also linear, then ultimately mu x is what? It is a linear combination of the input variables. So, it is just like a multiple linear regression model. Now, I am giving you a statement of this result without proof. Say any continuous function defined on R can be approximated by 3. So, you can use this equation to approximate any continuous function. So, thus a continuous function can be approximated by a multi-layer perceptron with a single hidden layer. A large number of hidden nodes of continuous sigmoidal nonlinearities, linear output units and suitable connection weights. So, this is the beauty of multi-layer perceptron. Even if you are using a single layer perceptron, that is a single hidden layer perceptron, a large number of hidden nodes of continuous sigmoidal nonlinearities and linear output units with suitable connection weights can approximate a continuous function. And if you increase the number of hidden nodes, then you get closer the approximation, better the approximation. Now, suppose we write B equal to beta I j, the ijth element of B is beta I j. So, B is T cross R matrix of weights between input nodes and hidden layer. So, in all you have T into R parameters in B, and A has j kth element alpha j k, and A is S cross T weight matrix between hidden layer and output layer. So, ultimately you have S t parameters in A. Beta naught is equal to beta naught 1, beta naught 2, so on beta naught t transpose. So, this is T cross 1 vector of parameters. So, it has T parameters, and then alpha naught is equal to alpha naught 1, so on alpha naught S transpose. So, this is S cross 1 parameters of bias. So, it has S parameters. F is equal to F1, F2, Ft transpose, vector of activation functions, and G is G1, G2, Gs transpose. So, both F and G are the vectors of nonlinear activation functions. F is the vector of activation functions at the hidden layer, and G is the vector of activation functions which you are using at the output layer. So, ultimately you can write mu k x equal to g k alpha naught k plus summation j equal to 1 to t alpha j k f j beta naught j plus summation m equal to 1 to r beta m j x m, and then we write this equation using matrix and vector notations. So, we can write mu x equal to g alpha naught plus a f beta naught plus b x. So, we are applying this activation function to reach the hidden layer, then you have these weights, and we apply this activation function to reach the output layer. Now, in this equation 4, GU is equal to the transpose of G1 U1 and so on GT UT. Actually, this G is a vector of functions, and U equal to U1 U2 UT transpose, this is a random vector. So, you have this random vector, and then you have applied this vector of activation functions. Further, mu x is equal to mu 1 x, mu 2 x, so on mu s x. Now, we consider a special case. Suppose both f j and g k, these are identity functions. Identity functions means f j x is equal to x and g k x is equal to x. Then what we get? We get mu x equal to mu plus a b x, where mu is equal to alpha naught plus a beta naught. In fact, in this relation, f beta naught plus b x is equal to beta naught plus b x. So, you get alpha naught plus a beta naught plus b x. Further, g alpha naught plus a f beta naught plus b x means g of this is equal to alpha naught plus a beta naught plus a b x. So, ultimately mu x is equal to this alpha naught plus a beta naught plus a b x. And then we are writing alpha naught plus a beta naught equal to mu. So, mu x is equal to mu plus a b x, and suppose you write c equal to a b, and the order of a b is s cross r. So, this c or a b is weight matrix for this single layer network. So, a neural network with a single hidden layer and sigmoidal activation function can be viewed as a non-linear generalization of multivariate reduced rank regression. In fact, notice that when you are taking the identity function, then mu x reduces to mu plus a b x, and then if you write c equal to a b, then this is actually linear reduced rank regression problem, which we have also considered in principal component analysis. So, when we discussed principal component analysis, we also discussed reduced rank regression problem, in fact linear reduced rank regression problem. Now, if you are using the sigmoidal activation function, then it may be viewed as a non-linear generalization of multivariate reduced rank regression. Now, we consider fitting of neural network. So, suppose x I is r cross 1 input vectors I equal to 1 to n. So, now you have training data, you have n independent copies of x's or n independent observations on x's, and yi's, these are the independent copies of s cross 1 output vectors I equal to 1 to n, and in all you have s t plus r t plus t plus s parameters. S t plus r t, the number of parameters which you obtain in the weight matrices A and B, and T and S, these are the parameters which you obtain in bias vectors. So, in all you have S t plus R t plus T plus S parameters, and suppose omega denotes the vector of all the parameters. Then basically what you want to do, you have to obtain omega, and for that purpose we minimize the error sum of squares with respect to omega, and error sum of square is summation I equal to 1 to n y I minus y I curl transpose y I minus y I curl, which is equal to summation I equal to 1 to n summation k belongs to capital K y I k minus y I k curl whole square. And here capital K is the set of all output nodes. So, that is why you are taking summation over the set of all output nodes. Y I, which is equal to y I k, is the true or target output S vector, and y I curl is the fitted output S vector. So, what is error? The true value minus the fitted value. Then y I k curl is equal to mu k x I omega, or you can write it as mu k x I. Ultimately, mu k is a function of input values as well as the parameters omega. So, mu k x I is the fitted value of the kth output node, and this kth output node is corresponding to x I, where I equal to 1 to n, k belongs to capital K. And this mu k x I is the final transformation of the vector of outputs. We have observed that how we get mu k x I. First we transform the input values, we get the hidden values, and then again we take the transformation from hidden to output, and ultimately you get this mu k. For the regression problem, you take mu k x I as the identity function. Now, we consider the multi-class classification problem. So, suppose capital K is greater than 2. So, the number of output nodes is greater than 2, and you have one value corresponding to each class. So, capital K is the number of classes. For classification, either squared error or cross entropy deviance are used. Say how we define cross entropy deviance? We take minus of log of conditional likelihood function. So, this is how we define the cross entropy function. E c omega equal to, we take minus sign here, then log of conditional likelihood function. So, ultimately you get summation I equal to 1 to n, k belonging to capital K, y I k log of y I k curl, where y I k is equal to 1 if x I belongs to pi k and 0 otherwise. Now, here z I j is equal to f j beta naught j plus summation m equal to 1 to r beta m j x I m. So, these are the values which we obtain at the hidden layer for j equal to 1 to t. We combine the input values using the weights betas, say beta naught j is the bias term, and then you have weights beta m j is corresponding to x I m. and then we apply this activation function, and then Z I is equal to Z I 1, Z I 2, so on Z I t transpose, and Z I naught is equal to 1. And then we define V I k equal to alpha naught k plus Z I transpose alpha k. So, we combine the values Z i's for the hidden layer, and we use the weights alpha k's, and then this is the bias term, and ultimately we get V I k's for all k 1 equal to 1 to capital K. Alpha k is equal to alpha k 1, alpha k 2, so on alpha k t transpose. So, this is t cross 1 vector, and then we take y I k curl equal to g k v I k, which is equal to e to power v I k upon summation L belonging to k e to power v I L. So, this is the final transformation of outputs, and then g k dot is the output activation function. Now, y I k curl is multi-class generalization of logistic function, and this is also called soft max function. So, here if you have just two classes, then you simply get the logistic function, and y I k curl is actually multi-class generalization of logistic function. Further, y I k curl is a non-linear function of omega. So, if you want to minimize the criterion like ESS or EC, then these criterion are also non-linear functions of omega. So, for obtaining omega, basically what you have to do, you have to minimize ESS or EC, and then of course, you won't get simple solutions. So, you have to apply non-linear optimization algorithms. So, we obtain the values of omega by using the non-linear optimization algorithm, and using these non-linear optimization algorithms we minimize ESS or EC, and we estimate omega. Then back propagation of errors algorithm, we compute the first derivatives of error function with respect to alpha k j and beta j m, and then we estimate the weights by minimizing the error function through an iterative gradient descent method. So, we will discuss this back propagation of errors algorithm in the next lecture in more details. Now, we consider this example of multi-classification problem. So, we consider Irish data set. So, we have observations on sepal and petal lengths and width of 50 flowers each of Iris santosa, Iris versicolor and Iris virginica. So, in all you have 150 flowers. So, these are the 3 flowers, and for these 3 flowers you have observations on sepal and petal lengths and sepal and petal widths. So, in all you have 4 variables, and using the multi-layer perceptron we classify the observations. Ultimately, you have 3 classes. So, it is a multi-classification problem. So, first what we do, we split the data into train and test set, and for that purpose in training set we take say 80% of observations, in test set we take 20% of observations. Or you can say that in training set we have 120 observations and in test set we have 30 observations. This data set is actually available in R package, and for solving this problem we use R package, and actually this data set is also available in R. Then the fitted model has two hidden layers. In the first hidden layer we have 4 neurons, and in the second hidden layer we have 2 neurons. So, we divide the data set into 2 parts, training set and test set, and then we apply multi-layer perceptron. These are the 4 input variables, and then these are the connection weights. Different connection weights are given here. In the first hidden layer we have these 4 nodes. This is the weight corresponding to the bias term, and then in the second hidden layer you have 2 nodes and the corresponding weights are given, and finally it classifies the flowers into one of the 3 classes. So, in all we have 3 classes: Virginica, Santosa and versicolor. This is the error, and the number of steps required is 566. For the model evaluation purpose, we use the test set. We predict the class of each flower in the test set using the input variables, and then we apply the fitted multi-layer perceptron with 2 hidden layers, etc. And ultimately we classify the observations, and we predict the levels of different flowers in the test set. And here you observe that 2 flowers are misclassified. 2 flowers of versicolor are misclassified in Virginica. So, model has wrongfully predicted 2 samples. So, it has 93.33% accuracy. You can further increase the accuracy if we add more neurons in each layer, or if you increase the number of hidden layers, but it may further complicate the model. So, the single layer perceptron which we have discussed in the last lecture are easy to interpret, but it has the limitation that if the classes are not linearly separable, then it fails. Often when you have big data and the relationships between the input variables and output variables is quite complex, then you cannot use single layer perceptron. So, in this lecture we have considered a generalization of single layer perceptron, which is a multi-layer perceptron. In multi-layer perceptron, along with the input layer and output layer, in between we also have several hidden layers, and each hidden layer is consists of a number of nodes. And how we compute the values corresponding to different nodes in a hidden layer? We use the values of the previous hidden layer or previous layer, and then doing the computations, we apply the weights, we combine the values of the previous layer using the weights and bias term, we apply the activation function, and then we get the value corresponding to this hidden layer, and this is how we move, and ultimately we reach the output node. We also discussed the multi-class classification problem. For the training the multi-layer perceptron, one can use back propagation algorithm, which we are going to discuss in detail in the next lecture. So, I am going to stop here. Thank you.
Hello and welcome to this piece of literary snippet. As a student of English literature, the kind of poetry that we are most likely to encounter is perhaps the sonnet. Now, a sonnet, as some of us might already know, is a poem which is composed by putting together 14 lines of verse, and this style of poetry was first popularized by a poet named Petrarch, who lived in Italy during the 14th century. Now, legend has it that Petrarch once saw a very beautiful lady by the name of Laura, and Petrarch was so enamored by the lady that he wanted to compose poems to celebrate his love for her. But there was a problem because marriage was impossible. Petrarch himself was an ordained priest, and that prohibited him from marrying. And the lady herself was a married woman. But nevertheless, Petrarch went ahead to immortalize the beloved and his love for that lady in poetry, and the form that he chose was the sonnet. Since then, sonnets have traditionally been written about ladies who are of unparalleled beauty, and about poets who are hapless lovers and who know that their love for their beloved would have to remain unrequited forever. Now, in England, the sonnet form came around 16th century, and its first practitioners were people like Sir Henry Howard, the Earl of Surrey, and Sir Thomas Wyatt. However, it was William Shakespeare who was to prove the greatest of English sonnetteers. And in fact, the charm of those sonnets that Shakespeare wrote 400 years from now still can be felt. And if I read out to you one of Shakespeare's sonnets, you'll appreciate this better. This sonnet is usually known by the title, "Shall I Compare Thee to a Summer's Day?", which is also the first line with which the poem begins. Shall I compare thee to a summer's day? Thou art more lovely and more temperate. Rough winds do shake the darling buds of May, and summer's lease hath all too short a date. Sometime too hot the eye of heaven shines, and often is his gold complexion dimmed, and every fair from fair sometime declines, by chance or nature's changing course untrimmed. But thy eternal summer shall not fade, nor lose possession of that fare thou owest. Nor shall death brag thou wanderest in his shade, when in eternal lines to time thou growest. So long as men can breathe or eyes can see, so long lives this, and this gives life to thee. Now, as you might have noticed, that very much like the Petrarchan sonnet, this poem too speaks of an idealized lover who is more beautiful than a lovely summer's day. But also notice how, in the last few lines, the poem subtly shifts from praising the beloved to praising the poet himself. It is the poet who is going to produce the lines of poetry which will preserve the beloved's glory forever. And people will continue reading them even after the beloved has died. As the last couplet of the poem suggests, so long as men can breathe or eyes can see, so long lives this. And here this, of course, refers to the verse that Shakespeare composes and which we are reading today, 400 years later. So long lives this, and this gives life to thee. Shakespeare is well known for these kind of subtle plays with the conventions, these kind of subtle reversals of what is expected conventionally. But nothing is more striking than the sonnets that he composed on a dark lady. In these poems, we do not meet the traditional fair, idealized beauty, but rather a woman whose appearance might even be described as ugly. Here is a sample. My mistress's eyes are nothing like the sun. Coral is far more red than her lips is red. If snow be white, why then her breasts are dun. If hairs be wires, black wires grow on her head. I have seen roses damasked red and white, but no such roses see I in her cheeks. And in some perfumes is there more delight than in the breath that from my mistress reeks. I love to hear her speak, yet well I know that music hath a far more pleasing sound. I grant I never saw a goddess go. My mistress, when she walks, treads on the ground. And yet, by heaven, I think my love as rare as any she belied with false compare. As you can see, the beloved described in this poem is nowhere as beautiful as a beloved of the first poem. Yet, the point that Shakespeare is making here is that though the image of the beloved is not as beautiful as it was in the previous poem, it doesn't stop her from being an object of love. Love, Shakespeare insists, has very little to do with the outward appearance of a person. And in many ways, this de-idealized beloved is perhaps a person with whom a more intimate engagement is possible. She is definitely a more human person, a person who treads on the ground just like all of us do. See you in the next episode of Literary Snippet.